Okay, so I will quickly run through what you need to know for interference. And specifically, I assume that you guys are already familiar with basics of waves. So this will be handling the harder part where we have to do more math. Okay, so firstly, you need to be familiar with complex notation and working in complex notation. So if you did not already know, you can express something called a complex number as in terms of a real number and an imaginary part, where this new imaginary unit I is defined as square root of -1, and therefore I squared would be just -1. So the other thing you need to know is that you can also express a complex number in terms of something we call the complex exponential. So I'll write the complex exponential as r e to the I theta. So um, visually, right, we can draw something called an Argand diagram. An Argand diagram basically is a diagram that has the axis of a real and axis of imaginary. So any complex number can be represented on the Argand diagram. How do we do that? We simply draw the complex number as a line, as this arrow, which we call a phasor. And then the theta corresponds to the angle our complex phasor makes with the real axis. And you might be able to observe here that tangent of theta will therefore be equals to y over x, basically the imaginary component over the real component. Uh, the reason this is very powerful is because in general, right, when we're working with exponentials, they are easier to add and multiply because you can factor stuff out nicely. And you will see later on why this is so important. And then the other equation that you need to be very familiar with is Euler's identity. So Euler's identity is basically something that you need to remember. It says that you can write e to the I theta in terms of a cosine plus I of sine theta. Okay, so this is just a very quick introduction into complex notation and working with it. All the rules for complex exponentials hold as usual exponentials. So let's say if you have e to the power of I theta, and then you raise it to the power of x, it still will just become I theta x. So rules like this for regular exponentials still hold. All the operations remain the same. It's just that now you have an extra quantity I. Okay, so the next part is how does this help us in real life? So how can we express an oscillation in terms of a complex exponential? So it's actually quite simple. In general, right, we would define waves or oscillations in terms of sines and cosines. So if I write x is equals to some amplitude cosine omega t plus some phase. So the phase is just the offset. It's just what is determined by the initial condition. So it just determines how it will move when against the time graph, the amplitude time graph. It will just move the wave left and right. Okay, so don't worry too much if you're not too familiar with what the phase is. And then we can notice that this cosine part looks eerily similar to our Euler's identity, because in the Euler's identity we also have a cosine part here. So we can actually write this in terms of a complex exponential. So we will write it as this. The real part of e to the I omega t plus phi. So if you compare this to Euler's identity, the theta will be our omega t plus phi, and you'll see that it will retrieve a cosine, it will give out a cosine omega t plus phi and an I sine omega t plus phi. But notice here that we're taking the real part. So when we do this real operator, we're basically just saying we want this part. This part, the imaginary part, we throw away, we discard it, okay? So in other words, we can just write x in terms of a complex exponential. And in general, right, for example, light is a form of EM wave. So EM wave, you can just simply represent it as E naught cosine omega t plus phi, right? Because it's just an oscillating electric wave. And then the magnetic wave corresponds similarly, it just differs by a constant. So both of them are sinusoids in that sense. And then we can also draw a phasor diagram with the exact same complex exponential idea. And then we can say that this is a phasor of our light, for example, and then the magnitude would be would just be E naught, and then this angle theta would be omega t plus phi. So it's rotating constantly in the um in the Argand diagram. Okay, so the next thing is we can actually add phasors. So by the principle of superposition, if we want to find the electric wave at one point, we can simply just add the two components. So let's say you have a double slit grating and they both hit a certain point. So there are two point sources. We will assume they are thin enough to be point sources. They are emitting light and both light hits a point on the screen. So I'll call the light from one E1 and E2. Note that E1 and E2 are functions of time because they are oscillating, right? So we can write the position E, the light over here, E, as just simply E1 plus E2 because of the superposition principle, right? And then we can do our phasor addition stuff. So I can do E naught e I omega t plus E naught e to the I omega t plus some phase shift. Okay, so the next thing that we need to talk about now is how do I determine what the phase shift is? So you guys might already be familiar with this formula, but for those who aren't, you can calculate the phase difference, I'll represent it by delta, is equals to the wave number, 2 pi over lambda, multiplied by the path difference, okay? So the triangle here is the path difference. So path difference is just the physical length difference. So if you think about it, right, this really is kind of like ratio of the wavelengths. So we can express path difference for double slit grating generally. If the difference between the distance is d, you guys might already be familiar. The path difference will be d sine theta, where sine theta is the angular position on the screen. So let's say if you're over here, and then the displacement will be theta. Okay, so this would then be our phase shift is equals to the phase shift. So I will elaborate further on this example. Let me add a page. So if we want to compute the intensity, last thing is how do we express intensity in terms of waves? So in general, you guys might already know intensity is proportional to the electric field, but first you need to time average it, okay? And then you square it. So basically what's going on here is that you need to first express the net electric wave. So E is equals to E1 plus E2. So you need to express it in terms of the sum of its components. And then once you do that, you must remember to take the real part before you do anything. And then once you take the real part, you can square it. Okay? So you take the real part of this, and then you square it. So E squared. And then the amplitude will be proportional to the E squared. And then after you square the amplitude, you take a time average. Okay, so this is the chronological order. First, you compute what E is. Okay, so you compute what this thing is. Then you take the real part, and then you square it. But as you do more questions, right, you'll realize, generally speaking, you don't need to explicitly do all these steps. Okay, the reason is because the real parts will present themselves very clearly in the question, and you can immediately kind of tell what will get cancelled out by the real operator and what will not be cancelled out. And then the time averaging, for the most part, will just introduce a proportionality factor of half, because you'll be time averaging something like sine squared or cosine squared, which both time averages to half. And generally speaking, we don't really care about this half, because what we will do is we will just write it. The question will just ask you for the intensity as a function of the max intensity, so I over I naught. So they ask you to express in terms of I naught. Then you can this is simply just E over E naught squared. Okay, so for the most part, right, you do not need to explicitly do the time averaging, taking real part, all this stuff. But the reason why I'm still saying it is because the question from the national team selection test last year requires you to do this step-by-step thing, because the question is slightly unorthodox. I won't spoil it. You guys can go see for yourself, but it requires a slightly unorthodox setup, which would need you to start from first principles. So it's very important that you understand how this thing works. So first, if you compute the sum of the electric field, then you take the real part, because the imaginary parts are non-physical. Then you square it and you take the time average, because your eyes cannot see so fast. You cannot possibly see like when the frequency of light is very, very high, as you guys might know. You can't see it oscillating. What you see is like a stable intensity. So you need to time average it. That's what the time averaging is for. Okay, but enough yapping. I'll just go through an example, a very simple example of the double slit version to show you how you can derive the intensity function as the intensity as a function of distance, angular distance. So if we are considering just the most basic setup of double slit, we are assuming point sources, so very, very thin slits. We're assuming they're separated by a distance d, and I'll define this angle, the angle to the horizontal as theta. Okay? So the way we'll approach this question is, we'll first write the electric field at this point, which is E. We'll express it as E. So E is equals to E1 plus E2, and E1 will be just E naught cosine omega t plus E naught cosine omega t plus the phase difference, right? And the phase difference phi, as we previously mentioned, is 2 pi over lambda d sine theta. Okay? So we can express this, we can convert it to our complex notation by simply doing, this thing becomes E naught e to the I omega t, right? And then this one will become E naught e to the I omega t plus phi. Remember, I'm leaving out the real part over here, but do remember at the end you need to do it. So we can further write this by factoring E naught e to the I omega t out. So we get this expression. So you might be wondering now, this is not really the answer yet, right? Because we still have these eyes floating around. So how do I deal with the eyes? So I'll propose a very important factorization trick, which is, generally speaking, if you can get one on, like in your term, right? You can get one on the left, and then you have e to the I something on the right. You can intentionally factorize it in a way such that you can extract real stuff out of it. So let me illustrate. If I factorize I phi over 2 here, negative I phi over 2, then it will look something like I phi over 2 sorry. It looks something like this, right? Like after you factorize it out. And we can actually use a property of sine and cosine, which is that if you did not know, sine x is written as, can also be written as e to the ix minus e to the minus ix over 2I. And then you can also write cosine x as e to the ix plus e to the minus ix over 2. So if you don't already know, you can write it like this. And we can simply invoke this identity to then express it as e to the I omega t e to the I phi over 2. And then this thing will just become cosine, right? 2 cosine I phi over 2. Sorry, phi over 2. Okay, so I'll give you guys a second to digest it. Basically, we did the first step is to sum up all the components, and then we factorized it in a way, in an intentional way, in order to invoke the identity, so we can extract some real quantities out of it. So for the more astute listeners, you might notice that if we defined our position from this point, so if we started here, then our phase difference will be phi over 2, right? Phi over 2 for the top, and minus phi over 2 for the top, and plus phi over 2 for the bottom. And then you would have to skip this factorization step altogether. You can immediately invoke the identity already, which is true. In most situations where there is symmetry, it might be smarter to define your angular coordinate from the point or along the line of symmetry. But you'll see that actually it doesn't really matter lah. In the end, like the function will still turn out to be the same. Okay, so moving on. Yes, so sorry, I got cut off. But what I was trying to say was that if you look at this term, right, we can do the next step, which is the real part, but you don't need to really do the real step. You can kind of tell immediately because you can write it as e to the I, and then you write omega t plus phi over 2 times 2 cosine phi over 2. So if you have a look at this, what we've written here, right, you should be able to immediately tell that like this thing will become I sine blah 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 in the bracket plus cosine blah 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 in the bracket. And the real part will eliminate the first thing, okay? So really, right, what we're going to be left with is 2 e naught cosine phi over 2. And then you have another cosine omega t plus phi over 2 after you take the real part. Okay? So I'll give you guys a moment to think about that. And like the next step would be to square it. So if we square it, we simply get 4 e naught squared cosine squared phi over 2 cosine squared. Okay, I'm a bit lazy, so I'll just write omega t dot dot. Okay? The whole point is now we time average it, right? So we do the time averaging thing. And you will see that, like I said just now, the cosine term will like fall out. Okay? So in the end, right, in the grand scheme of things, we could have simply just wrote I is proportional to E magnitude of E squared, right? And then the reason is because this will introduce a factor of half, but because we're talking about proportionality, it doesn't really matter. Okay? So we really only care about what this factor is in front. I know the cosine square time averaging will introduce a factor of half, but you generally speaking for convention, we just keep this whole thing because it's more complete. And then we can write I as a function of theta. So I'll erase this. So we don't need to explicitly do the time averaging because we know that time averaging cosine will reduce to a constant. And we'll write this as I of theta over I naught. Okay, so I naught is the maximum intensity, the central brightness. Okay, and then it's this thing squared. So you will soon see that it is just 4 e naught squared cosine squared phi over 2 over e naught squared. And then the e naught squared and e naught squared will cancel. So we can write the final function I of theta as I naught as 4 I naught cosine square phi over 2, where phi is equals to this stuff on top, 2 pi lambda d sine theta. So it's simply the 2 and the 2 will cancel, pi over lambda d sine theta. Okay, so 2 pi lambda. Okay, so we can also check that this makes sense because as you guys would just know from regular like H2 physics, like summing out the path difference and stuff, you should know that the maxima will correspond to d sine theta equals m lambda, right? where m is like an integer. So we can check that. You can check that when m is 1, 2, 3, 0, 1, 2, 3, blah, 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 cosine squared would correspond to a maximum, right? Because cosine squared is like this, then you can check that it will correspond to a maximum. So we know that this intensity function is correct. In general, right, so you guys, if you are more observant, you might notice that if you do the time averaging here, right, it should introduce a factor of half. So half times 4 the prefactor will become 2. And then you might think that um, you might think that shouldn't this be 2 instead of 4? So here's the thing. Generally speaking, the markers will mark for what your term over here is, because that is the most important thing. This one is defined by like your initial conditions. Initial conditions. So it's not really that important. And also, the other thing is that at the maximum intensity, it is 2 E naught, right? Like technically speaking. So there are a lot of like weird stuff that has to do with this prefactor. So in general, I just ignore it. But the learning point here is mainly that you can derive the factor in front. Okay, so to summarize, right, what you need to know, you need to first, the steps are first, you need to write E as a function of E1 plus E2, potentially plus E3, and so on. Sometimes they can give you a diffraction grating. Diffraction grating has infinitely, or not infinitely, but many, many slits. So you need to sum them all up. Step 2 is to take the real part of E. And like I said just now, once you do enough questions, you will soon kind of get a feel for it, and you don't need to explicitly go and write out the whole function and choose the real part. You can immediately kind of tell what is real and what won't be real. And then step 3 is you need to square this thing. Right? And then you take step 4 is you take a time average. Okay? So you take this thing, square, and then you take a time average. And most importantly, time averaging of sine square omega t plus whatever constant phi is equals to time averaging of cosine blah blah blah, and this will give you half. Okay? So the prefactors, perhaps not that important. I think you can still figure out what the exact prefactor should be, but you need to remember to consider not only like at the maxima is 2 E naught, but also the fact that when you time average, there'll be a half introduced. So I think personally, I think the prefactor is not that important. The marking point will not be what the thing is in front. It'll be more of what the function is in the function as the function of distance of angular displacement. That is the more important thing that they will mark for. But if you track very carefully, I think you can figure out the exact prefactor. Even though personally I don't do it because I think it's not worth the time. Like I don't think they mark it. Okay? But I would like you guys to now give it a try by doing this question. And there are two methods to do this. First is by integration, and second is by summing. Okay? So if you do summing, right, you will notice that it will become an infinite sum. So the summing method works by discretizing the whole slit into many, many small slits, into n small slits. And then you perform a sum for like a very large n, where n approaches infinity. And then it'll become a geometric progression, and you can use the GP formula. Okay, and it might be useful to use the factoring trick and then to apply the sine and cosine identities. So I'll leave this for you guys to work out yourselves. Okay, hope this helps.